Thank you. Thank you for coming to this talk. I'll just give a quick introduction. So it's going to be something very, very basic. But it's about the guard pattern, which is a neat design pattern that I've found myself using sometimes when writing Rust code. So just gonna like present it, say when it's applicable and when it's a good idea to use it. So I'll start with a motivation, which is basically the mutex, and then give some real use cases, and then some more remarks about it. So when it's applicable and when you should be careful about it. So I'll start with the mutex, which is a motivation. So yeah, the scenario that we have is that we have some data on the heap, so it's shared memory, and we have two threads that are trying to access the data. And obviously you cannot do these uncontrollably because otherwise you would have data arrays. So what we need is some kind of synchronization method. So in this case, we have a mutex that protects the data, and then the threads need to use the mutex to actually access the data, and the mutex is gonna control when the different threads actually have access to the resource. So what we would like is something like this, where you have both threads trying to get to the data, so they call this acquire method. The first one, like the lucky one, gets mutable access to the data. So mutable means exclusive, so that's why it's mutex. And eventually, when one of the threads is done with the work, then the resource is unlocked, and the other thread that has been waiting the whole time can get access and do its thing. So basically, what we need is an acquire method. So forgive, like the syntax is clearly not very specific nor correct, but bear with me. So what we want is this acquire method that basically you call it while the mutex is locked. It just spins wait or whatever, just hangs there until eventually the lock is removed. So only at that point you set yourself locked and you get access to the resource. And then obviously we also need an unlock method, which is going to be called when you're done accessing the resource. And in this case, we just say, OK, like the mutex is free, so the next one can access it. So obviously, there are multiple problems with this approach. The first one is, well, I mean, we would like to get exclusive access to the resource. So normally, when you get a exclusive reference to something, you're probably like passing a mutable reference to begin with, because you're going to say, I'm the only one that has access. But clearly in this case, this is not going to work because you have two threads calling simultaneously. So this signature is already funky. And so that means that we're going to expect some shenanigans, which is going to be either unsafe or interior mutability, stuff like that. And also a bigger problem, which is here we are essentially expecting the caller to be a good citizen and call the unlock method when they're done accessing the data, which obviously is not going to happen. Yeah, so an improvement we can do on this design is, OK, so as we said, we need interior mutability because we need the mutex to be called by multiple threads simultaneously. So the mutex needs to be borrowed in a shared way. But we still want to get something which represents the fact that we have unique access to the data. So what we're going to return here is not a mutable reference to T, but is this object called lockGuard. And you see that the implementation of this acquire method is identical. So we still wait while the mutex is locked, and when eventually it's unlocked, then we set it to lock, and we get the lockGuard. So the promise that the mutex does is that it's only going to return a lockGuard that is alive at a time. So you cannot have two lockguards around simultaneously, because that would essentially be equivalent to having two mutable references at the same time. Then this object, this lockguard object, is in place of a mutable reference to T. So it just implements the refmute. So you actually have access to the resource as long as you hold this lockguard. And finally, we implement drop on this lockguard. So when the lockguard goes out of scope, or in any other situation where it's dropped, then we unlock the mutex. So the diagram here looks exactly the same, essentially, but instead of getting shared mutable references, We just pass lock guards around, and there's no one that's responsible for calling unlock, because it's the lock guard itself that's gonna unlock the mutex. So that was the motivation for the guard pattern. So I'm gonna quickly define it more properly. So I'll start with RAII, which is an idiom that means resource acquisition is initialization, which is a property of a type that essentially says that holding a value, a valid resource is an invariant of that type. In particular, it means that the object is created with valid data, and the memory that supports it is valid and is handled properly. So in particular, this means that the memory is allocated properly, the data is written in there correctly, so while the object is alive, the memory is fine and the value is correct, and everything is cleaned up when the object dies and the memory is freed. Obviously, this is kind of a design choice of Rust, where most types satisfy this property. Not all of them, obviously, because there are some selected instances where you want maybe the thing to not be properly initialized or to contain proper valid data. You have maybe an init for that. And other cases where you don't want necessarily to run the destructor, or you don't want to free the memory, or you don't want to drop something. Those are valid scenarios, but those are specific examples. Usually, the normal types satisfy this property. So the classic example of this is boxing. So here we have an object, the box, that lives on the stack, but it manages some data that lives on the heap. So what happens here is that when we construct a box, we provide some value, which is the value t, and what the box does is it's responsible for managing the memory and also representing the fact that you are the only owner of the data and you are responsible for cleaning it up. So in particular here, we see that when we construct the box, it just allocates a memory in the heap, it puts the data, a fully constructed, fully valid data, in that memory location, and you get the box back. So while you hold the box, you know that the data is fine, the memory is fine, and you take the responsibility for cleaning everything up. And again, that's done in the drop, where we drop in place the thing that's in the heap, because obviously you can have that the thing on the heap is itself managing some other memory. So that data is cleared, and we also deallocate the data that we, the memory that we had on the heap. So a guard is kind of a refinement of this property, or is an object that follows a specific kind of RAII. So we have this object that manages some kind of resource, which could either be data or an abstract resource like a behavior or some property. And it also provides compile time proof of some invariants. For instance, for the, well, we're gonna see later. Yeah, here. So for instance, for the lock guard that we saw a second ago with the mutex, what happens? So we have that the lock guard itself represents proof that the mutex was locked. So as long as the lock guard is around, we are providing guarantee that the mutex is locked. Just like if you get a mutable reference to something, that guarantees that you're the only one that is currently accessing it. But that's given by the compiler. Instead here, this is given by having the guard. So by essentially enforced by RAII. The lock guard also manages the data or some property. In this specific case, you have access to the underlying resource, and you're the only one that has access to the resource, so that avoids data races. Also, we have some nice guarantees given by the compiler. In this specific case, you have a lifetime, so we know that the lock guard is, well, the mutex is gonna live longer than lock guard, so while you have the lock guard, the mutex cannot be dropped, and you cannot be left with like invalid memory or something that is not allocated or initialized. And finally, the lock guard releases the mutex when it's done its job. So now I'm gonna present some practical use cases that we found, that we've seen around. So this one, we use it at our company. So the idea is you have a mutex, but instead of accessing data on the heap, you access data on a database. So again, here you have generic tasks. So I'm not going to say threads here, but you have tasks, and you use this PGMutex to access uniquely and mutably some resource on a Postgres database. So the diagram is essentially the same because it's just going to do the same job, just on a different context. And so what we have is acquire, and here you see that basically we have a connection to the database, and what we're going to do is we're going to set an advisory lock, and this is equivalent to the mutex spin locking, spin waiting. Here we just connect to the database, and the database is going to respond when the lock is successfully acquired. So this relies obviously on some feature on Postgres, but the idea here is that after you've managed to set the advisory lock, then you can say, well, I do have access to that resource and no one else should be writing to it. And we do that by essentially handling all mutations through this lock guard that is returned by the previous method. So here specifically, we're gonna say, yeah, well, I'm gonna update the value that is on the database. And then finally, when the lock guard drops, then we release the lock on the database. So this is really a contrived example, but is a simplified case of what we actually do. So we use this pattern in the event sourcing RS library that is open source, and we use it at our company. That's the source code if you want to see it. And yeah, so what we do is we essentially implement pessimistic locking when we have an aggregate stream, so that you know that you have access to the aggregate, you're gonna apply a command and write the events, and no one else is. So here I've kind of commented out most of the code, but I just wanted to showcase that it's not super complex, but it's not super simple either. But the important bits here are that you take the aggregate, you take the ID, you construct an advisory lock key, and then again, use the connection to ask Postgres to set an advisory lock for that. And then when you're done, so when the await point continues, then you know that you've acquired the lock. And that object actually is a bit tricky because it must contain both the lock and the guard. But you see that the guard there is a bit weird because it has a tick this lifetime. So you know that there's going to be some self-referential shenanigans. Because yeah, at some point we had to capture both the connection and the information about the lock. So everything is going to be packaged there. And so this PG store lock guard is self-referential. There are some weird things that you need to worry about. And also probably unlocking the advisory lock on Postgres is going to be an asynchronous operation. So you have async stuff in drop, a bit tricky. So I'm not going to go into details, but not everything is super easy as it seems. So while using this thing, we've learned some lessons, which are, well, as the implementation that I've showed here uses acquire that essentially just hogs the connection until the database eventually returns, which could mean that if you have multiple connections all trying to access the same resource, you're gonna basically starve your threads or starve your task or whatever, and they're all gonna be stuck waiting for the thing to be free. And one point is learn from standard, because this is a very known problem. Mutex, the standard mutex, has a try acquire method that returns immediately. So instead of blocking until you get the resource, you try acquire. If you're successful, you get it immediately. Otherwise, it fails, and you can retry, you can abort, but you handle it without essentially starving your connection pool. And more in general, synchronization usually is hard. So like you want to pick the right tool for the job. And we implemented this pessimistic locking when we had low contention, not many accesses to the same aggregate. So it was an easy way to avoid optimistic locking or other strategies. But obviously, if in more complex scenarios, if you have high contention, you're probably better off with an optimistic locking, which means that you try to write, and if anything, you fail writing the event after the fact. So that introduces other complexities, but obviously there's no silver bullet for everything. Okay, so another scenario, which is the kernel scope guard. So there's nothing special about the kernel here. It's just a scope guard, but I found it neat that it's also used in the Linux kernel. Well, in a library that is used in Linux. So that's the source. Here I'm gonna just show a simplified example. So we have this thing called scope guard that you see is just a wrapper around a function once. So essentially, it's just a closure, right? So we wrap a closure. We optionally wrap a closure. So when you construct this object, you need to pass essentially a closure that you want to invoke. And that closure is executed on drop, assuming it's still there. So that's why it's wrapped in an option. Because, for instance, in this particular case, you also want to have a way of dismissing or disarming the guard. So the idea is you want to always execute a closure as soon as the object goes out of scope, unless you've dismissed. But obviously, this is a design choice. You can also have it so that it's always running when it goes out of scope. So you wouldn't even have the option. So an example that's taken from the repo is here. I mean, it's pretty easy. Like, you create this scope guard that's called log, and its job is just logging, right? It just prints out something. And you see that in the code, you have some early returns, and at the end, there's a log dismiss. So what's happening here is that this scope guard is going to be invoked every time you return early. So you're gonna see the log printed in the first return point or in any other early return. And then if you go to the very end where you've disarmed the callback, then at that point it's not going to log anything. So this could be useful for, I don't know, if you want to log if there were some errors that made you abort the function, or if you have some kind of like unlocking of resources or whatever. So basically handle the unhappy paths in an automated way, because you see that in none of those points we actually had to explicitly log anything. It was just done automatically. Another thing that this scope guard does in the kernel crate is that it can also manage data. So for instance, here we constructed this scope guard with a vector, with an empty vector, and the closure at the end, it just prints out the number of elements, right? So here, for instance, in this example, it puts something on that vector, and again, if it returns early, then it's going to print out, in this particular case, it's going to print out that it has one element. At the end, you add another element, and then you just go out of scope. So here we're not even disarming, we're just letting it do its job. And so when the guard goes out of scope, it just prints out the number of elements. Okay, so some final remarks. So there are some caveats associated with this pattern, which is, first of all, drop is not guaranteed to always run, because obviously in Rust you have affine types. So the destructor is going to be invoked at most once, but there are ways to prevent that. For instance, if you leak, so if you forget an object, if you wrap it in manually drop. So there are ways to avoid running the destructor, which in this case would invalidate the whole point of having a guard. And also, as I mentioned earlier, drop doesn't play well with asynchronous tasks at the moment. We'll see. But yeah, so if you need to perform asynchronous cleanup on drop, it's going to be a bit tricky. And yeah, just a final summary. So again, like you have a guard, and that provides proof of some invariance for the data or behavior that they manage, and it's tied to their life cycle. And they guarantee automatic cleanup when they go out of scope, or for instance, if there's a panic. So if you want to have some kind of automated behavior when your code path exits, then a guard is a good idea. And that was it. Thank you.